All right, so today what we are looking at is it's called exploring and travelling. So the exploring aspect of it's um, not quite sure why they actually put that in there, but basically it's just moving around a network in a particular way, and so travelling, exploring the network in a particular way, travelling through the network in a particular way. All right, so there's a few things, few definitions here to go in your definition summary for your band reference. All right, so you're working through this. So walks, here's a walks, is the next one on your list. So a walk is a sequence of edges linking successive vertices in a graph. Um, so a walk starts at one vertex, follows any route to finish at another. All right, so you kind of have to take these um, definitions a little bit literally, all right, because there's some subtle differences between them. So if it doesn't mention something, then you don't need to be concerned about it. So in this one here, sequence of edges linking successive vertices in a graph. All right, and it starts at one vertex, follows any route to finish at another. All right, so if that is the case, here's an example. I might start here. All right, and so I might decide I'm going to go down there. I'm going to go up to here. I might swing around, come back to here, and then I might then decide to go here, and I might decide I'm going to finish there. All right, so that's one example of a walk. So through a sequence of edges, so these go along the edges, which are the lines, of course. So there's a sequence of edges there. Starts at one, follows any route, so any route could go anywhere, and finishes at another. All right, so there's the walk. Trail. Trail is the next kind, and the trail says no repeated edges. So it's a walk with no repeated edges. So the walk thing, when we got here, all right, starts at one vertex and finishes the route at another. So for the next one there, the trail, we can't have this bit, all right, because this bit here we've got a repeated edge. So no repeated edges. So if I wanted to, I could start here and I can come around back here like I did before, but now I can't turn around and go back. I have to go through a different. All right, so here we go, and I might decide I'm going to come and I'm going to finish here. All right, so I've started and finished at different vertexes. I've followed edges, and I haven't repeated any. There, of course, there would be, plenty of others as well. All right, a path is a walk, no repeated edges, so this is adding an extra layer on each time, and no repeated vertices. So here we've got a repeated vertex here. We've got any up here? Yes, we have there as well. All right, so we can't repeat a vertex. So we can walk anywhere we like. Let's start here again. So as I've started up here, let's go. I can go around there, go around there, go around here, and there we go. Let's finish up here. All right, so I haven't repeated any edges and haven't repeated any vertices, so that there will be a path. All right, the next one is a circuit. All right, so things with a circuit, so it's a trail. So trail meaning no repeated edges. So that's why this definition sheet's handy, and you need to be able to find it quickly in the exam, because there's just slight differences, subtle differences between these definitions. So it's a trail. So when we go back up here to trail's a walk with no repeated edges, all right? So that's what in the brackets there. So it's a trail, so we don't repeat edges because it's a trail. Starts and ends at the same vertex. All right, so starts and ends at the same vertex. So for example, let's pick here, we're starting up here. It's a trail, no repeated edges. So let's go here. Here's an example. We'll go down here, let's go down here, let's go up here. Let's go and finish up here. All right. So that's just one. There is others. Now it doesn't mention anything here about for trails about vertexes. So I could have, from hit this point here, I could have come in and then back that way. All right. So for a circuit, you can repeat edges, but not. Repeat vertexes, but not edges. Now, if you want to not repeat either of them, and I've kind of already done one of these here, so and that's a cycle. So cycle, you can't repeat edges or vertices. All right, so up here I probably should have, done a little bit of a different circuit than I did there as an example. But so say my circuit, I could have gone down here, down there, back to here, and then up there. All right, so that's a circuit. All right, no repeated edges. Cycle though, we don't have repeated vertices either. All right, so here we might start here. Oops, start there. Let's go down here. Let's go across here. Let's go, and then we've got to finish back up here. All right, so we haven't repeated any edges. We haven't repeated any vertices. So that's then what we call a cycle. All right, so let's identify what's going on here. So in this first one, part A here, what have we got? So we start here and we're going down around there. All right, and back to where we started. So there's no repeated edges. Really, but we've been through C twice. So C is repeated. And what do? We start and finish at the same spot. All right, so from the definition there, it's got to be one of these last two. It's got to be a cycle or a circuit. The difference between these is there's no repeated edges or vertices for a cycle, but a circuit, just the edges not repeated. So that means this first one here would be a circuit. All right, so in this one here, slightly different, but this one we've got no repeated edges, no repeated edges, no repeated vertices, and we start and finish at A. So this one here then, because we've got no repeated vertices as well, is now a cycle. All right, then the next one we come to, we start and finish at different places. So this is going to be some sort of a trail, a walk or a path. It's not going to be a circuit or a cycle because they start and finish at different places. All right, so what have we got? Any repeated edges here? Doesn't look like it, but we've got, so no rep edges, but we got here repeated vertice, and they start and finish at different places. All right, so we'll come back to our definitions. We've got to repeat it, so it's not a path. No repeated edges, no repeated vertices. No repeated edges for a trail. So a trail is what this last one, what this next one would be. All right, so we've got a trail here. Oops, trail. Let's get rid of that. Not a trape, a trail. No repeated edges, but a repeated vertice. All right, now this last one here, look. Yeah, all right, start here. We go down here, around there, around here, back again. So repeating this vertex, and then we're going up here, so we're repeating this. So we've got a repeated vertex and a repeated edge. So that's then, if we go back up to the top, the one that's got no, so it's a walk sequence of edges linking successive vertices. All right, starts at one vertex, follows any route, finish at any route. All right, finish at another. So that last one's got to be a walk. All right. So there's those particular ones. So now we move on to particular types of trails and circuits. Here's our friend Euler. So Eulerian trails. Now this definition. So again, you can go in your definition here, but in your definition sheet, there should be another word here to really be clear. An Eulerian trail follows every edge of the graph once. All right. That important bit there, they leave that out. So in the textbook, which is where I copied this from. So that really should be there. So then there's a couple of things that, so you've got to have a connected graph. All right, because you've got to go through every edge once. It's got to once, right? So it's got to be connected for a start, because you're going to get from one part of the graph to the other. And exactly two vertices have an odd degree. All right, so Eulerian trail. So let's have a look at an example here. I've got some. There we go. Let's go, and that's A here, B, C, and D. So odd degree, so it's a degree 1 there, 1, 2, 3, odd degree there, 3, 1, 2, and 2 there as well. All right, so it seems like, and it's connected. So how can we go around this? Well, we can follow every edge of the graph once. So we've got to come, we can go here, we can come around here, we can go around there and finish there. All right, so I can go that way, that way, that way, and around that way. And that then satisfies those requirements. All right, there's another one. You could go around the other way as well. But all right, so you've got to have two vertices that have an odd degree. All right. Next is an Eulerian circuit. So for an Eulerian circuit, it follows every edge. So it follows every edge. So here for Euler, edges, Euler E, edge E. All right. So again, follows every edge, starts and finishes at the same vertex. All right, so Eulerian circuit will exist if it's connected, has all degrees, even degrees. an Eulerian circuit can begin at any of the vertexes. And so a note, if graphs have more than 2 odd-degree vertices, neither an Eulerian trail nor an Eulerian circuit exists. So let's have a look, for example. So to get an Eulerian circuit, this would have to be modified. And so what I'm going to do is I'm going to draw that same one again. So we've got up here, down here, up there, back to here. So A, B, C, and D. But then they've all got to be odd, so I'd need another connection around there between A and B. And so now we can start and finish at the same place. So let's start at A. We can start and finish here by following each of the edges once. There's one example. And then, so we start here and finish there. All right. So Euler, edges, all got to have even degree. All right. So as you can see, I put that loop in here, changes that from 3 to 4, and that from 1 to 2. So that's Euler. So I already mentioned Euler edges. So for Eulerian trails and circuits, it's the edges that are important. Now Hamiltonian is about vertexes. All right. So a Hamiltonian path. And I'm going to use the same diagram as I did for the Eulerian. Oops, I had them around the other way, I think. A, B, C, and D, or did I have D and C? Let's have a look. C and D. That's it. All right, A, B, C, and D. So all you have to do is you visit every vertex of the graph, and again, it's once. It's an extra word there. It should be there that I'll have to put there. So there's 2. You can start here, up, boom, boom, and then finish. And now every vertex there has been visited, and once. All right, we're going to visit the A, B, C, and finish at D. Of course, you could go A, B, D, and C as well. Now, cycle, of course, we need to start and finish at the same place. But here, with Hamiltonian stuff, you can only visit the vertexes once. All right, because we don't repeat vertexes. And here's a Hamiltonian cycle. Every vertex starts and ends the same. And so there's no Hamilton, before we had odd and even vertexes that helped us with Eulerian. Unfortunately, we don't have that with Hamiltonian. We've got to inspect and have a look. All right, so let's have a look. So I'll draw the same one again, but again I'm going to have to do a modification, but it's a different modification. So here's my A, B, C, and D, but it's got to be a different modification because I need to get back. If I start here, so let's start here again, and I follow what I did above, and I went around here. Now I need to get back to A, but I've already been through B, so this would need another edge to take us from B back to A. And so then we can shoot around here and finish at the same vertex that we started. All right, so for Euler, edges, no repeating of the edges. Hamiltonian, it's vertices, no repeating of vertices. All right, what have we got here? So let's have a look at some examples. All right, so I should have put this in, but I haven't. So So for following, determine if an Eulerian path or circuit. So we're looking at Euler path circuit. All right, and the first diagram looks like this one. There's our vertices. They're all joined, and then we've got these up here. All right, so when we look at this, all of these ones on the outside have all got degree 1, and all of these ones here all got degree 3. So all our vertices are odd, and remember we can only have 2 odd vertices. So there's none possible. Okay, because to visit everything, we would need to double up on our edges. All right, so if we started here, we go down here, and we get to there, and then the only way we can go and visit all the edges is to double up. All right, so the next one is this diagram. So we've got A, B, C, and D, and we've got some edges. A is connected to B, it's connected to C, it's connected to D, it's connected back to A, and we've also got a connection across here, and we've got another connection here, and then we've got another connection all the way around there. All right, so the question is here, can we get a Eulerian path or trail? So we've got to travel across around each one, and only once that we travel edges. We don't have to necessarily start and finish. So let's start here, for example. Let's go down here. Let's shoot all the way around here to A. Let's swing around here. Let's then swing around back here. Swing around here on the edges once, swing around here, and then finish up there. All right. So if we looked to begin with, which I didn't, you'll see that we've got C and B that are both odd. So we've got 2 odd. So C and B odd. So 2 odd suggests that we can get a path, an Eulerian path. All right, and then I've drawn that. All right, so all the edges we can get to and travel across once. All right. All right, the next lot of diagrams about Hamiltonians. So Hamiltonians, paths or circuits. All right, my notes, of course, I've scanned those and they're on the website there, Physics with Synno, just underneath this, Synno's notes. So there's a bit more detail of the diagrams in there. So I forgot to scan them. All right, so this time Hamiltonian paths or circuits. So remember, Hamiltonian's to do with the vertexes. Now we can't, no repeat vertexes. All right, so we can repeat edges. We don't need to necessarily go over all of the edges, but we've got to go to every vertex without repeating. All right, so we've got this first one. We've got these 4, A, B, C, and D. and the connections between them are like this. So the question is, can we... Oh, and there's another one around here. Not that we need it, I don't think. So we've got to visit every vertex. So let's have a go. Let's start here. And let's go down here, around here, and then back to where we finish. All right, so we've got a circuit going on here. So we've got a Hamiltonian circuit here on this one. So that's all good. All right, this next diagram. So I've got some points here, one there. I've got 3 here. That's nice. One there, and so A, B, C, D. Let's call this one E. Very boring and go. All right, and there's the joining up. So can we travel through every vertex once without repeating? Now, the problem is we've got this one hanging here in the middle. These 3 here hanging in. So I could go there to there to there, but then I've got to repeat, so that's no good. I could go from there to there to there, and then I've got to repeat again. So it's looking like, all right, what about if I go this way? I can come here to here to, and then I can't. Yeah. All right, so it's looking very much like with this one, no possible. So because not possible, none possible. Because it's too, I can't write spell, but anyway, let's not worry about my poor spelling. It should be BLE, not LBE. So either A or C must be repeated if we're going to visit everyone, which of course we know we're not to be doing. All right, so yes, none possible, no Hamiltonians possible there. And the last one, is a bit longer and a bit more involved. We've got all of these points, so A, B, C, D, P, D, E, F and G. And connections, these are connected, like so. Then we go across here to D, then we go on up here, across there, down there, around there, going across here, and then we go to G to C shortcut. All right, question is, what can we do here? Can we go through every vertex without repeating? And I would say that we can, and there's probably a couple of different ones here. So let's have a look. Let's start here and back to here. Let's go around to there. Let's go to here. Let's go around there, and let's finish there. And we've now travelled through every vertex once, which is what Hamiltonians is about, travelling through it once. So we've done that, but we're not back to our starting point. So it's not a circuit, so we've got here a Hamiltonian trail. All right, so there's a fair bit of theoretical stuff going on there. So now we move on to exercise 14C in your textbook. And if you've got any questions, make sure you ask me for clarification if you need it. All right, have fun.